What's going on, Falcons? Mr. Mac here. So next week's topic is on the sun. So I figured I'd show you some of my own personal sun pictures. Some of these pictures are of the sun and sunspots. Some of these pictures are of different eclipses, lunar and solar eclipses. We'll talk about what those are. And I also have some pictures of transits, and we'll talk about what a transit is. So without further ado, let's go ahead and get started. Let me share my screen here. Share screen. All right, you should see a nice picture of the sun there. Now this picture here of the sun is not a recent picture. This picture is a picture that I took about 6 years ago during the last solar maximum. We have that nice big group of sunspots right there. We haven't had a group of sunspots like that on the sun for a few years. So again, during solar maximum, we have a lot more sunspots. And right now we're during a solar minimum. We're deep in the minimum. So that group of sunspots that you see there right here is about the size of Jupiter. So it is huge. You could fit 10 Jupiters across the diameter of the sun. You could fit 110 Earths. You could actually fit 1 million Earths inside of the sun. So the sun is big. Now, as you're doing your research, you're probably finding out that the sun isn't a very big star compared to some of the other ones out there. It's a middle-aged star. It's right smack dab in the main sequence on the HR diagram. But this picture does give you a good idea of what big sunspots and big sunspot groups can look like. So let's go ahead and move on to the next picture here. All right, so this next picture here is actually a picture of the sun that I took with a specific camera for astrophotography. It allowed us to kind of zoom in on the sun. Matter of fact, we zoom in a little bit more here, if it lets me, there we go. You can actually see that the sun is not a smooth surface. It actually kind of has this grainy texture to it. And if this was a video, which I at one time did record a video of this, you could actually see the boiling or the movement. And these little graininess is actually called solar granulation. This is where the convection currents of that superheated material are coming to the surface, kind of like a boiling pot of tomato soup or a boiling pot of water. The hotter stuff rises and it cools, it sinks back down. And these cells are causing this kind of grainy, bubbling kind of structure called solar granulation. So phenomenal image, but then again, great coloration there. You can see that the sun in this image is actually yellow. Our sun is a yellow star. It is a G-type star. So just, when I go back to this photo here, it still has that yellow color, but sometimes depending on the type of filter you use, you might get a different picture. Now this picture of the sun and this picture of the sun were taken by using a Mylar filter, which allows you to look at all the visible wavelengths. So this is how the sun would look if you could actually look at it without burning your eyeball. Now this picture here though, this is that hydrogen alpha. So that gives us that nice red sun. Now the sun is not red, okay? But we're looking at that specific wavelength, the hydrogen alpha wavelength, which hydrogen alpha's in the red end of the spectrum. And that's why we're looking at the sun. We're looking at the sun's lower atmosphere called the chromosphere. So we look around the edges, and I'm not seeing anything here particularly, but sometimes you can see a prominence or a solar flare coming off of the edge. There's a little bit over there and some over here. But again, this kind of allows us to see how the sun's atmosphere acts. Now, the next picture here is a picture of the moon. Now, great photo here. If you look at it, you can see all the Mare, which are flood lavas, flood basalts. When the moon was impacted, a crater was made, and that crater filled in with lava. So you can see all the different lava features here, different impact craters. Those are the younger areas on the moon, the lunar lowlands. And then here, there's bright areas down here. You have the lunar highlands. Nice impact crater there. But this is the side of the moon that we always see. We never see the far side of the moon from Earth. The only time we've ever seen the far side of the moon is when we sent spacecraft back there. So like my Saturn V rocket, which sent the Apollo astronauts to the moon. So if we go to the next photo, you're probably asking, why are we looking at a picture of the moon when we're supposed to be talking about the sun? Well, we're talking about a lunar eclipse. So this right here is a picture of the moon during a lunar eclipse. Now, a lunar eclipse occurs when you have the sun and the earth and the moon, okay? And the moon travels behind the earth and goes into the earth's shadow. Now, a lunar eclipse can only happen during a full moon. And it doesn't happen every full moon because of the way the moon's orbit is tilted around the Earth. So, here in this case, the sun and the Earth and the moon lined up, allowing us to get a lunar eclipse. Now, right here, it's not completely covered, but right here it is. So when the moon passes completely in the Earth's shadow, that's when you get this brilliant reddish orange color. And that reddish orange color is actually caused by the atmosphere of the Earth. As the sunlight hits the Earth and it goes through the Earth's atmosphere, it gets bent. And if you remember, longer wavelengths of light are red and orange. So that red light gets bent and hits the moon, giving the moon that nice reddish orange color. If we didn't have an atmosphere, the moon would go completely black during a total lunar eclipse and then come back. But because of our atmosphere, we get that nice reddish orange hue. Now, this is a kind of a time lapse that I took of a total lunar eclipse that was on December 20th of 2010. And you can see here, there it is, the full moon. But as it goes through or starts passing into the shadow of the Earth, you can start seeing the Earth's shadow right here. And notice the curvature of Earth's shadow because the Earth is a sphere. So there you go, you get that curvature, just a little bit of sunlight, and then bam, right there. Now the eclipse started right at about 9:59 p.m. Mountain Standard Time, and it went into final totality, like when the moon completely went in the shadow of the Earth at 1:10 a.m. So it took about 3 hours for the moon to fully go in to the Earth's shadow. And then this right here at 1:45 is when the moon was right there in the middle, that dark red. It's amazing to see that. Now, a lunar eclipse lasts much longer than a solar eclipse, total solar eclipse. The reason is the Earth's shadow is much larger, so the moon passes through that much larger shadow. But the moon's shadow on the Earth is much smaller. So that's why it happens much quicker. We'll talk about a solar eclipse here in a second. Here's another group of photos that I took during a lunar eclipse. And right here, the eclipse started right at about 11:22 p.m. And then you start seeing the shadow of the Earth starting to hit the moon. And at about 1:08 in the morning is when we had totality. So about 2 hours later. Now this one went into the shadow, and there you go. You can see that nice reddish color again for your total lunar eclipse. So a lunar eclipse is when the moon passes into the Earth's shadow. So this right here is a video, actually kind of a sequence of images that I took of a solar eclipse. Nice big group of sunspots there, but we'll watch it here and you'll actually see right there. That is the moon. So a solar eclipse is when the moon passes in front of the sun. So you have the sun, you have the moon, and you have the Earth. And the moon passes in between the Earth and the sun, casting its shadow on the Earth. So remember, lunar eclipse is the Earth's shadow on the moon, and a solar eclipse is the moon's shadow on the Earth. So we'll do that again so you can see it. And this was not a total eclipse. This was a partial eclipse, but you can see the moon nicely moving across the sun there. Now, this, as you can see, was about, I would say, 50 to 60% covered. And you could notice just a little bit of change in that daytime sun. It was pretty cool. So this actually happened during the day at school, so we were able to watch it happen. So it was a nice little treat. So actually, this is a picture of that same eclipse. Just right smack. Again, there's that nice big group of sunspots. But one thing I want to show you with this image is if we zoom in a little bit, you'll notice that this is the moon right here. This part right here, that dark curved part, that is actually the moon. So you're seeing the moon and you're seeing the sun. But I want you to look at the edge here. Do you notice that the edge is not perfectly smooth? Well, the moon's surface isn't smooth. You're actually seeing all the crater rims and mountain edges and valleys of the moon along that edge right there. So you can see them. I mean, that's why it's not smooth, because the moon has mountains and craters and canyons and valleys, and you can see it right there. It's pretty awesome that you can see it in that photo. So this is a picture that I took of an annular solar eclipse. Now, an annular solar eclipse occurs when the moon passes in between the Earth and the sun. So in this photo, this dark circle here is the moon. But we talk about it in class, how the moon's orbit around the Earth is not a perfect circle, okay? The moon's orbit around the Earth is not a perfect circle. When it's close to the Earth, we call that perigee. When it's further away from the Earth, we call that apogee. And it varies by tens of thousands of miles. So when the moon is at its furthest distance, or apogee, it doesn't completely cover the sun. So we call that an annular eclipse. So this was down in New Mexico a few years back, and the moon's just starting to get in there, and you can see a little bit right there still. It was pretty cool. It looked like the sun was like Pac-Man. It was eating up the moon when this type of eclipse happened. But that right there is max eclipse. So you have the moon right there, and you have that ring of sun around the moon, kind of, sometimes we call it the ring of fire in a solar eclipse. It's still not safe to look at, actually. You still have to have special glasses and a special telescope to look at an annular eclipse, because you're getting still about 5% of the sunlight hitting the Earth, and it's still pretty bright. So I had to use a special filter to take this photo here. Now, this is the same eclipse. You can see the moon starting to cover the sun there, but this was taken in that hydrogen alpha filter again. But what's great about this photo, if I zoom in, you can actually see right here a little bit of solar prominence. And a solar prominence is the sun's gas leaving the surface of the sun, following the magnetic field of the sun. If you look it up, solar prominence, you'll see some beautiful examples of solar prominences. Sometimes you get these big loop prominences that can be several Earths in size. And that's just the sun's gases following the magnetic fields between sunspots. So beautiful, beautiful image there in hydrogen alpha. So let's see what we got for the next photo here. Yes, great. Okay, so this is kind of a whole kind of put together montage of that eclipse. And this was the annular eclipse, May 20th, 2012. I actually drove down to New Mexico with my kids, stayed the night at my friend's parents' house, and it was awesome. It was sunny all day. We go out of the city, out of Albuquerque, where there was going to be the best viewing, just like 30, 40 minutes. And there was one cloud in the sky, and it was over the sun. I'm like, are you got to be kidding? I've been waiting my life for this, literally 3 decades. And right as the eclipse began, right at about 6:15, that cloud moved away, and the eclipse started. So we were very lucky. Like, seriously, one cloud in the sky, and there you go. Notice though, it's much quicker. From right as the eclipse was starting to like right in the middle of annularity, or I can't say totality because it's not a total eclipse, 7:34. So just over an hour. Think about how long it took for the lunar eclipse to happen. Lunar eclipse took much longer because the Earth's shadow is much bigger. But the solar eclipse here is much shorter because the moon's shadow is much smaller. So there you go. Kind of a neat little cycle there. So 6:17, you see the moon kind of getting swallowed up by the sun. Now the moon's completely in the sun there, and now the moon starts to depart. Now we never got to see the whole eclipse because if you look up here, the top picture there is at 7:58 p.m. and the sun was setting. So I'll show you that picture a little bit later, an eclipsed sunset. It was pretty cool. Actually, I had to haul butt back to Denver the next day because I had to get back in time for graduation. So it was fun. Get out there, see the eclipse, drive back. I love it. So this is actually one picture that I took of another solar eclipse. But this solar eclipse, hopefully you got to experience. This was the eclipse of August 2017. I'm not even joking. I have been waiting for that eclipse ever since I was a kid. I remember sitting in my parents' hallway, looking through my dad's astronomy books going, when is the next total solar eclipse? August 2017, I'm there. So I literally had been waiting like 3 decades for this eclipse, and I wasn't gonna miss it. So we hopped in the car, the family, all 6 of us, we drove up to Nebraska. Unfortunately, I was worried about the clouds, so we jetted over to Wyoming and Torrington, and we got the eclipse. So this is right before the moon completely covers the sun. Now here in Colorado, you got about 97%, which is awesome. But the difference between 97% and 100% was literally night and day. It's like someone turned off the sun. And this was that split second right before totality when you get that diamond ring effect. And I was so excited to be able to get this photo. This picture here was taken with a filter. And I took it's like my grandfather, who was a photographer, it's like nudged me. He's like, Bob, take off the filter. So I took off the filter, took the picture, got that right there with that diamond ring. What's cool about it though is if you look closely, you can see these little pink areas right there. Those are solar prominences, like I was talking about in the hydrogen alpha picture. So you have just a little bit of sunlight left, and then you get totality, which was just phenomenal. If you ever get a chance to see a total solar eclipse, go. And I hope some of you got to see this one. I believe the next one is in 2024. And it's going to kind of go through the East Coast, kind of East Coast down through Texas. Get out and see it. It is just a mind-blowing experience. Probably one of, if not the coolest astronomical thing I've ever experienced in my life. You could feel it get cool outside. Like, I am like, oh man, should I put on a hoodie? No, I can't. I'm not going to miss this. And it was unbelievable. And again, you can see those solar prominences there on the side. Look at those nice loops, just beautiful. This is a picture I took with my iPhone, and you see it right there. I mean, it was like sunset in the middle of the day. You had this 360-degree sunset, and then right up there it is. You have the sun, and the only time you can see the sun's outer layer is right here during totality, and that halo you see around the sun is called the corona. It is the outer atmosphere of the sun. It comes from the word crown because it looks like a crown. So there you go. That's the only time you can see the outer layer of the sun's atmosphere is during a total solar eclipse. So that was a pretty cool thing to see right there, to see that eclipse and that 360-degree sunset. And here's kind of a time lapse, if you would, or again, another montage. Here we are at 10:22 in the morning. And then we see the moon passing in front of the sun. And then right before totality, 11:53, and then boom, totality. Mid-eclipse was at 11:48, so about almost an hour and a half after the eclipse started. And again, remember, you can have a lunar eclipse, and totality can last 40 minutes during a lunar eclipse. But during a solar eclipse, this was 2 minutes. 2 minutes, it's all we got. It was fast. Now, theoretically, the longest solar eclipse you can have is, I believe, 7 minutes. So that's it, 7 minutes. Because we're looking at a very small shadow. I think in this part of the United States when this eclipse was happening, I think you had to be within a 60-mile range to see totality. If you were out of that, you wouldn't. During a lunar eclipse, a whole entire hemisphere of the Earth, like the Western Hemisphere, all of North America, South America, can see an eclipse. So very different sizes of shadows. And the eclipse was all done at 1:15. So there you go. So excited I got to be able to see that eclipse. Now, what if you were on the moon or on the space station observing a solar eclipse? This is what you would see. This is from an Earth observing satellite, and you can see the daytime. You see there's nighttime, and then I'll hit it again. So here's daytime, and now all of a sudden you see that shadow of the moon move across the Earth. That's what it would look like if you were in a spacecraft orbiting the Earth, or if you were on the moon. And this was not the 2017 eclipse. This is a different eclipse, but it is a pretty cool view here. There it is. And all of a sudden you see that shadow of the moon move across the Earth. So there you go. That's pretty amazing. And if you're just outside of that shadow, you don't even see the eclipse. All right, let's see what we got next. Just a fun little cartoon. What really happens during an eclipse, and you have the Earth taking a picture of the sun, and the moon, boom, photobomb, there you go. So I like that. I thought that was pretty funny. Oh yeah, let's talk about transits. So the planets can never all line up. All right, they all have different orbits. You know, Mercury goes around the sun every 88 days. Venus is like 240. Earth is 365. Mars is 687. You get all the way out to Pluto. Pluto takes 248 Earth years to go around the sun one time. And then not all their orbits are around the sun's equator. Some of them are slightly tilted. So it's impossible to get all the planets ever to line up. But sometimes you can get maybe one or two. In this case, we have the sun. Now we have some sunspots. That's a sunspot. That's a sunspot. But that black dot right there is actually the planet Mercury. So every few years, decade or so, and then a little break, Mercury actually passes in between the Earth and the sun. We call that a transit. So I'm going to kind of go through a couple pictures. So there's Mercury. Watch what happens. You'll see it move. Oh, now there's Mercury. So it was here, and now it's here. And then one more. There it is on the very edge right there. So let me back it up. There you go. Now you can actually watch the planet Mercury move across the disk of the sun. This takes a couple hours or so. Mercury's fast. It's going around the sun every 88 days. And again, you have to have a special filter to be able to do this. You should never look at the sun without the special or without the proper equipment. You can cause permanent eye damage. So I have a special filter that allowed me to take these. Even during a solar eclipse when the moon is covering the sun, you should always wear protection. A lot of people can have permanent damage. So special filter allowed me to get this image of the transit right there. And then again, we'll watch it. There you go. That's Mercury. Now, the other planet that does it is Venus, but that's a little more rare. A Venus transit occurs about every 110 or so years. And the last one was in 2012. So unfortunately, nobody alive today, unless you live to be like 100 and some, will ever get to see a transit of Venus. And during a student trip to Hawaii, we actually got to see that 2012 transit of Venus. Now, this is not the transit. This is just a really cool photo that I took of the planet Venus there and the moon. Venus has been brilliant in the night sky. Brilliant. It's up right after sunset. It's that bright star-looking thing out in the western sky. And check it out. And actually, in about 2 or so weeks, let's see, what is today's date? Today's May 6th. So in about 2 weeks, you have the crescent moon starting to rise up again. Actually, a little more than, actually, no, it should be about 2 weeks. And it'll visit Venus. It's really cool when you get an alignment of the moon and Venus like that. Now, if you look really carefully in this photo here, you can see the whole moon. This is the part that's being lit up by the sun, okay? And this right here, still the near side. We only see one side. This right here is, well, you know, people like to say the dark side of the moon. Now it's just the nighttime side, okay? This is the side that's not being lit up by the sun. But sometimes when the moon is just a crescent, you can see the night side of the moon. And the reason why is because the sun is hitting the earth and the reflection of sunlight on the earth hits the moon. And we actually call this earth shine. So I encourage you next crescent to see if you can see the earth shine. It's pretty cool. But this right here is the transit of Venus. So again, there's the sun. These are some sunspots right there. Let me just kind of zoom in here. So you can see the sunspots right there. And that black dot right there is the planet Venus. Now, look at how much bigger the dot is. I gotta find, this is the Mercury dot, okay? And this is the Venus dot. So Venus's dot is much bigger. Mercury's like 3,000 miles in diameter. Venus is almost the size of the Earth. It's almost 8,000 miles in diameter. Plus, Venus is much closer. Venus can be 25 million miles away, I believe, 25 to 30 million miles away. Mercury is like, I gotta do my math here. It's like 60 or so million miles away from Earth. So Mercury is going to appear smaller because it is, and it's further. Venus is going to appear larger, well, because it is larger and it's much closer. So now this is a picture of that Venus transit. Now it's fun is I got a bunch of photos here, so you can actually watch it move across the disk of the sun. Now, if you notice, the sun actually changes a little bit color. This picture here was taken around noon. So it's much higher in the sky, much clearer. And these photos here were taken at just before sunset. The transit ended just before sunset in Hawaii. So there you go. So that's mid-transit right there. And you can see the planet Venus moving across the disk of the sun. So unfortunately, unless you live to be really old, you won't be able to see the transit of Venus, but you will have an opportunity to see transits of Mercury because they happen about every decade or so. We just had the last one, so the next one won't happen for like another decade to 12 years. So there it is. That's a transit of Venus, and this is the transit of Mercury. It's kind of like an eclipse, but we call them transits because you're not completely covering up the whole sun there. Now we see eclipses kind of like eclipses on other planets. So let me show you some examples of that. This next picture here is actually a picture of the sun from the planet Mars by the Curiosity rover. Curiosity is roving around on the surface of Mars. And it happened to catch the moment that one of Mars's moons, Mars has two moons, Phobos and Deimos, the time that Phobos actually passed in between Mars and the sun. So it's kind of a mini, it's like an annular eclipse. So it is a solar eclipse, but Phobos isn't big enough to cover up the whole sun. Actually, you can kind of see, it's not even spherical. It's a city-sized rock, much more like an asteroid, but it still orbits Mars, so we call it a moon. But that's pretty cool. The Curiosity rover was able to see that eclipse. Now, this is the planet Jupiter, and this was taken by the Hubble Space Telescope, and Jupiter has a lot of moons, like 60 plus moons, but has 4 really big moons, okay? It has Ganymede, Europa, actually it goes Io, Europa, Ganymede, and Callisto. Io and Europa are about the size of our moon, and Ganymede and Callisto are about the size of the planet Mercury. But what's great about these Hubble pictures here, for example, this right here is the moon Io, so you can see Io right there, and that is Io's shadow. So if you were standing right there, you'd be seeing Io blocking out the sun. But what's really cool about this picture is you actually have 3 shadows. You have the shadow of Europa to here, the shadow of Callisto here, and then Io's shadow here. Now here's Callisto, around 3,000 miles in diameter. So the sun angle is shining over here. So that means the sun in this picture is down off to the lower left. Europa's not even in the across the face of Jupiter yet, but in the next picture over here, you have Io. Io's shadow is no longer visible, but you have Callisto. It's moved on a little bit more, and you can see Callisto's shadow there. And then here, you have Europa, and then Europa's shadow. And it looks like, even if we look closely, we can see some, oh yeah, look at that. Some of the smaller moons of Jupiter. There's the moon Phoebe and its shadow. And then the moon Amalthea, and then its shadow. So that'd be pretty cool to see multiple shadows because you had all these moons. So that happens on Jupiter. Saturn also. This is a Hubble Space Telescope picture of Saturn. And this is Saturn's moon Titan. And it's also larger than the planet Mercury. And that's the shadow of Titan right there. So it's really amazing when our solar system lines up. It does some pretty special, spectacular things. So I hope you enjoyed these photos. Have a great week, and we'll see you later. Mac out.